Next talk will be given by Vladislavs Bezrukovs on overview of VIRAC facility and science based on it. So Vladislav, please.
Okay, thanks. And thanks for everyone to visit Ventspils even virtually. And I hope in some day you will visit Ventspils in person as well. And I try to give overview of our center. Yes, maybe continue discussion about the possibility of radio observations. Maybe one of my topics and interests from our center to advertise our instruments and bring these instruments to community and possible find some collaboration and use of our telescopes. So this is maybe one of our ideas to make a bit advertisement of our center. So first of all, we are from one side rather young center, from another side not so young. We are located near Ventspils in Latvia, in Baltic Sea shore, and our history starts in 50s. The secret Soviet military space center was established in Irbane site near Ventspils. Was really secret, and some people from Ventspils, local people, even told what they didn't even know what such kind of object is located in 30 kilometers to the city. And in 60s, end of 60s, 70s, two parabolic antennas with diameter 32 meter and 16 meter. Now we call it RT32 and RT16 was built in this place. And of course, my main goal is spying for satellites and Western communications. After 94, after the Soviet Army withdrawal, and antennas was become property of Latvian Academy of Science. But in this time, telescopes are heavily damaged and no documentation at all. So in this time was established VIRAC, Ventspils International Radio Astronomy Center. We have two antennas, but they was completely not operational. And in this time was formed a small group of engineers and radio astronomers and astronomers that tried to convert these old antennas to radio astronomical needs. And in 98, first antenna movement of RT32 was done, and first radio astronomical observations was done. And one of them also exactly solar observations. Later, in 2004, VIRAC merges with Ventspils University College and becoming part of Ventspils University College. Currently, so in 2010, two institutes, so Engineering Research Institute and VIRAC merged together, found our original institute, Engineering Research Institute, Ventspils International Radio Science Center. And currently we are not Ventspils University College, but Ventspils University of Applied Sciences. And main directions of VIRAC, as Alexei Klokov, our director, already told, it's rather wide. So it's radio astronomy, astrophysics, and space studies, and I'm mostly focusing on these directions. But also we involve remote sensing group, satellite technologies and electronics, and high-performance computing. And high-performance computing at this moment mostly operates for astronomical needs to astronomical data processing. And our infrastructure is administrative buildings are located in Ventspils, and in Irbane, 30 kilometers away from Ventspils, we have our observatory. So it's two antennas, you see here, 32 meters and 60 meters, administrative building. And also from 2019, we have LOFAR station, LOFAR Latvia. Now it's operational. And it takes a long to renovate our antennas. As I told, in 90s, antennas was heavily damaged. And in 10 years after we got antennas, we have working on old equipment. And only in 2010, 2015, we have administration, Latvian and European, give us money for huge renovations. And we managed to renovate our surface of big antenna. You see here, so it's take a lot of time, and renovate control system, completely remove old one. You see how it looks before in 2011 and 2008. Old motors, old control systems, rather semi-automatic control, semi-manual control. But after renovation, we got a new modern control system and automatic control. And again, old motors and replace it with new motors, very precise, and give us opportunity to make a positioning of our antennas with very big precision. Also, we equip our antennas with all front ends and back ends needed for radioastronomical works, including 2 active hydrogen masers needed for VLBI observations. And now telescope control, so it looks our control center and control screen. It's fully, let's say, remote telescope, remote robotic telescope. So we have operators who control telescopes mostly from or went to university or even from home. RT16 was heavily damaged in 90s, and we have to completely remove old antenna and put a new one, carbon fiber antenna at 16 meters diameter. And it was 2015, 2016. In this time, it was one of the biggest carbon fiber antennas in the world. So in first 10s, I think. Again, so you see here new antenna and old antenna. Now it's in our museum. Looks like a UFO landed in our site. And again, it's antenna equipped with recording system and receiving system. And you see here how it looks before renovation. Old control system, a lot of wires and dirty. And after renovation, it's more pleasant to see. And currently, antennas are fully operational in range. So RT32 equipped in receivers up to 8.8 gigahertz with possibility to work up to 22 gigahertz, and RT16 again equipped with receiver up to 8.8 gigahertz, but in future we're interested to upgrade it up to 40 gigahertz. Both antennas are equipped with broadband cryogenic receiver system operating in 4.5, 8.8 gigahertz. So a similar system in both antennas. Each receiver is divided in subbands, around 1 gigahertz big. Additionally, RT32 equipped with L-band receiver in frequency ranges 1.4, 1.72. It's offset system made by our engineers, fully made in our house. 2 polarizations, and also it's warmer. It's not cooled, but still do a lot of science with this receiver as well. Additionally, we have specialized microwave spectral polarimetric observations and spectral polarimeter, but I probably not stay in this slide because next talk by Dmitry Bezrukov will cover solar direction of our instrument, of our telescope. But solar observations, as I told, historically started maybe first in our center and continue previous heritage from Baldwin Observatory located in Latvia. Currently, I try to highlight what kind of activities we have in our center. And for example, in 2021, we have several observational campaigns. In observatory, we have a procedure for time application. So if you would like to observe, you have to fill proposal for observations, and our time allocation committee grant or usually grant time for your observations. And for last year and this year, main topics of our observations is galactic maser projects and galactic maser observations. Maser flares and VLBI observations and light VLBI so-called using two antennas and in interferometric mode. Additionally, we try several years to find out major in comets flying nearby. Next, huge activity is variability properties of Seyfert radio galaxies, Perseus Alpha and similar, together with Latvian Ukrainian collaboration. Additional direction is application of forward scatter radar method for detection of space debris. So using interferometric methods, trying to detect space debris and possibly asteroids coming from some direction. One big international collaboration, our antenna participate in fast radio bursts detection together with Inava EVN antennas. This takes a lot of time, but in this year is quite highlighted by good results, and I show some pictures later. And one of big direction also solar microwave spectropolarimetric observations of Sun with Urban radio telescope. And one also big direction is interferometric observations together with our antennas from Europe and world, including so we are part of European VLBI network, and in this activity participates RT52 and RT16. And if looking from hours, so in total, we allocate around 5,000 hours for both antennas and LOFAR as well for this year, but still we have a lot of free time for observations. And it's almost same, so it's measures, fast radio burst, interferometer, VIRAC observations, and active galactic nuclear and sun observations. Recently, we got interesting collaboration with Czech Academy of Sciences, and it was attempts to observe multivalent observational campaign of Cygnus 61, and we try to find out flares from Cygnus 61 and got some good results as well. Some images of sun observations. I think Dmitry will show same and discuss it in more details, but we able to map sun with our RT52 because our star beam size is rather small compared to sun's sizes, and some images how it looks sun from our RT52 in two frequencies. And as I told, we have a new LOFAR station, LOFAR Latvia, and we are interested to do research in a single station mode, and got some first results observing Cygnus Alpha and Cygnus Cassiopeia Alpha, and currently try to find out how we can adapt our LOFAR observations for ionospheric scintillations and cosmic wave studies, and some examples of similar studies from Ukrainian UTR-2 telescope done in 2010. As I told, we are deeply involved in European VLBI network, observing in 4 bands, L band 1.6 gigahertz, 5 gigahertz, 6.7, 8.4 gigahertz. Around 1,000 hours of observation time is granted to EVN. Maybe one of the good results of this collaboration is proposal what was obtained at time for EVN telescopes by Artes Aberfeld, and some nice results with Aberfeld and company produced in last year and this year about major observations, and compared to single station observation as well, and mapping of major cloudlets. As I told, major observations are historically maybe second longest for our telescope, and currently we have more than 5 full years of monitoring of major sources. Around 30 sources are observed constantly. So, and in several, even 2 years ago, I think, we also participate in a project trying to discover new excited age majors, and found several new candidates in this direction. Additional direction related to major observations, we try to find out if major lines can be observed with our telescopes, and spent a lot of hours trying to catch comets and to measure lines from comets. Unfortunately, finally, we find out that our L-band receiver is good, but not good enough to catch possible major lines. And currently, we are going to improve our L-band receiver to make a cryogenic one, and continue studies in new sensitivity level. And some examples of major lines seen from our telescope, just to show how noise level can be achieved with RT32 with L-band. One of a big direction is active galactic nuclei research and variability of AGNs. Last year was very intensive collaboration with Ukrainian and Slovakian observatories, and we managed to make international team of combining results from our telescopes and also Zolochev telescope, Zolochev 32-meter telescope here. It's also old communication antenna, but last year the Ukrainian colleagues managed to convert it to radioastronomical instrument, which is very interesting, and we got exclusive access to first observations, even in test mode, but still it got very nice results. Additionally, we combine our radio observations with optical observations using Slovakia and Baldone in Latvia observatories. Also very nice, interesting results. Unfortunately, we can't find radio optical correlations, but we found a lot of periods and variability of our data. Next big topic, and probably very interesting for stellar community, urban interferometer. So as we have two antennas and both equipped with interferometric instruments, receivers and backends, masers. So we can use our antenna as a interferometer and raise our sensitivity and reduce noise and RFI. And we tried last year, but currently our antenna at T32 is in next stage of renovation, hopefully ends very soon. And we try to continue to use our interferometer for different kind of sources, possibly also stellar studies. And one of the next topic, which is very interesting for space safety, is detection of asteroids and space debris using interferometric method and using so-called forward scattered radar method. When we have a transmitter, black body, and antennas catching signal going through transmitter and black body. In this case, we are not interested of properties of black body. We just need to know or estimate its size, and possibly can detect it in any condition, even completely dark in radio. In this case, we use GPS satellites as transmitters, and space debris and space station and aircraft as targets to prepare and establish methodic sort of data processing to try to find out how it works. And this method, yes, in English.
Sorry, Slava, you have 5 minutes left.
Okay, yes, I almost finished. Yeah. Last years we made several experiments and finally got interferometric reflections and forward radar scatter reflections. You see here like a fast and slow motion two signals coming directly from transmitter and coming from target crossing transmitting signal. So method shows that this is possible, and currently we try to find out how to go to next step and try to make it in lower frequencies using low far field. Next good and promising topic for our studies. In this case, we are not doing studies, but we provide our instruments is pinpointing repeating time sources, fast radius bursts, and it takes around 4 years. But currently, in this community, we got definitely find out what we found several tens of repeating fast radio bursts and positioning them in high accuracy, in arc seconds accuracy. And in this experiment was involved several antennas, around 15 antennas together from Europe, China, America, and so on. And if we're looking for time consuming, in this case, Urbane provided for this year's most, not saying most valuable data, but biggest amount of data for observations. And finally, it was published in Nature this year, so this result was accepted in high level. I think I will stop here. We have a lot of infrastructure projects now and try to find out how to improve our instrument, and particularly T32 to equip with new receivers and new higher precision surface to make its surface more accurate to rise working frequency. Ongoing work hopefully ends next year, probably next summer. So additionally, we also will put L-band in cryogenic regime, so and will be more sensitive and better instrument. So I think I skip ESA activities because we're also involved in ESA studies and ground studies to make a RT16 not only receiving station but also transmitting and working with deep space communications activities. Yeah, so this is also ongoing in our directions, but I think I'm not having time. If you have any questions, we can discuss it a bit later. And yeah, so I think I can skip this one. Thanks for timing, and I have probably a couple minutes for questions.
Again, yes, thank you, Vladislavs, and you have actually more than a couple of minutes, so you've got 6 minutes for discussion. So, who wants to begin, please? Any comments?
Gavin
Question?
Ramsey, raising hand.
Oh, really? I didn't see it. Okay, Gavin, if you did, so please go ahead.
No, it was just a clap.
All right, that was a clap. Okay, there's appreciation.
Thank you, thank you.
Yep. All right, so questions, comments? So, Val, please.
Okay, maybe just a couple of technical questions. So first of all, what is the data policy, say, of your institution? So are the data sources in the open access, or so the only access is via collaboration?
Observed data, I think, mostly in the hands of PIs of the projects. So actually don't really have data policy in this case, because all of the data are more or less done by observers, and we physically don't have publicly available old data. But if you're interested in some old results or old measurements, we can think how to find out it in our archives.
Yes, I see. And maybe a follow-up question. Do you have any kind of catalog of targets or say observation times? No, for example, for solar observations, sometimes we need so confirmation of some, we'll say, quasi-periodic pattern or something like that, so with a different instrument. If there is a catalog, we can simply check whether your, say, telescope or telescopes were observing so the sun during so the period of time of interest. Do you have this online, or it should be just say?
It should be. We have journals of observations, and in this case, we have to find out for proper journal date and find out what is kind of observations are done in such a period. I think for major observations is more or less settled, and it's better have structured so we can easily find sources and timing. For solar observations, I think it's not so good establish it as a logging. We have observations, and probably Dmitry Bezrukov, the next speaker, can show it in more details. So if you have any questions about exact observations, you can ask Dmitry to share or describe this data.
I see. And maybe so.
Yes, we can discuss it a bit later because it is. Sorry.
Yeah, please. Okay, we'll discuss it later. And maybe just a third quick question. Are you aware of any systematic artifacts of your instruments, like systematic jitter or some other, say, artifacts which should be known before so the data is analyzed?
So we try to, if we found some problems, we try to fix it in fast as possible.
No, I'm not talking about some transient kind of difficulties, but I'm talking about some systematic, like, for example, the Nobiyama radio heliograph was known to have a significant jitter. So when a strong radio source was situated near the solar limb, and it was an intrinsic feature of the instrument, and we had just to deal with this artifact. But no,
I say no information. So if someone from observers found that we have such kind of jitters, we of course can put it in our website. But currently, I would say it's not or not found or not existing in this case.
So
okay,
what is
thank
the minimal sensitivity of your, say, RT32 observations in, say, millianskis?
I would say if we're using RT16, it's less than Jansky. So RT32 around half Jansky.
Half Jansky?
Yes, if you're speaking about interferometer, it goes to 10-20 milliansky.
Okay, thank you.
So thank you both, and for a good discussion as well. So, and we have one more question from Ivan. Yeah, one more question from Ivan. So Ivan, please go ahead.
Yes. In one of your slides, I saw you mention about lightnings on some planets. Can you show it again, please? I just would like to.
So it's idea what we can do with our. Wait a second. About our LOFAR station, because in single LOFAR station we can use it to find out lightings from Jupiter, and I think it stopped. This not proven yet, so what we can do it. So we have several tests, but I think not real result about lightnings from Jupiter. But as we know, this is possible with LOFAR, and it's should be possible with our station. But we have, if you're interested, we can try in more deeper and to try to find out how we can organize it.
Okay. Do you have plan to observe lightnings on Venus?
We can try. I think first of all, it was probably so only 2 slides with low fars, so it should be somewhere here. We never try to observe lightnings in Venus, but we can try with low fars. So if they are strong enough, we can try to find out if we see them.
Okay. I just asked because we have some project in our institute for spacecraft which will go through Venus, and one of the scientific tasks there is to try to detect signature of lightnings. So, but it's not so much known about that. So I'm just interested. Did you already measure them, or this is just in plan? Yeah. Okay.
No, this is plans, and this is some results from Ukrainian telescopes, UTR. So it's similar to LOFAR, but in this case, from one side rather old, from another side more sensitive.
Yeah. Okay. Thank you very much. Maybe later.
And here, Ivan, you see, so it's a Saturn lightning, not Jupiter lightning. So in the caption. No, in the caption to this figure.
Here is Saturn lightning, but we think Jupiter should be more stronger, and we definitely have to see them.
Yeah, but probably on Venus it should be not so strong. But okay, Jupiter also interesting because we are also going to Jupiter. Okay.
So, but yes, we can discuss it later. Yes.
Yeah. Okay. Thank you.
Okay, nice discussion.